Good morning. We're on to Lesson 2, Notes, Exponential Growth and Decay. Yesterday we just did an introduction of what an exponential function looks like and different properties of an exponential function. Today we're going to get into word problems using exponential functions. So a little reminder, an exponential function is a function of the form y equals a times b to the x, where a is a constant and b is greater than 0. And we learned yesterday that when b is greater than 1, the function will represent exponential growth. And when the b value is between 0 and 1, the function will represent exponential decay. So in other words, with exponential growth, your graph will look something like this. It starts off very slow and then grows very rapidly. And with exponential decay, it's the other way. You start with all of your substance or whatever it is, and it breaks down until you have almost nothing left in a very quick manner. So this is our general formula for word problems with exponential functions. It's the same thing, but our exponent x is usually a fraction, t over p. And then I've broken down what each of those stand for. It'll be easier to go through an actual example. I'll kind of read through it. Y is the total amount of whatever you're looking at. So if you have a certain substance and over time it either breaks down or it multiplies very quickly, y would be what you end up with at the end. A is the initial amount you're starting with. B is the multiplication factor. Usually it's written in words like a half-life, doubling time, triple, that kind of thing will always be your B. T is the total amount of time that has passed in the question, and P is the time it takes for the bacteria or whatever to double or half or triple. But again, it makes more sense when we kind of go through an example. So let's look at the first one. So what I like to do first is organize my information. So I always write out, these are all my variables available to me. And then I like to read the question and then kind of fit it in where it goes, and it's way easier to fill in your formula. So it says a culture of bacteria triples every 25 hours. These are your B and P value. Your B and P value are always closely linked. So if it says triples every 25 hours, this is your B value, and this is your P value. And they're usually grouped together. Triples means 3. So my B value is 3, and my P value here is 25 hours. I like to write down the unit for my P because you have to be careful. If I have another time, I have to make sure it's also in hours or the formula won't work. Then it says initially there are 1,000 bacteria. Your starting amount is always your A. So my A here is 1,000. So that's all I know from that first statement. Now it says for part A, write an exponential function that models the given conditions. So when you want to write an exponential function, it's like you're writing an equation for it. You're going to end up having 2 unknowns there. So you have all the information you need. Here's our basic form of the equation. So now I'm just going to fill in what I know. My A is 1,000. My B is 3. T I don't know yet, but my P is 25. So this is going to be an exponential function that models the given conditions. Now it says how many bacteria will there be after 5 days? This is now your T value. It's telling me the total time that's passed is 5 days. I know it triples every 25 hours, so how many will I have after a total time of 5 days? So when I think of T, I think it's the total time that's passed. You have to be careful here, and this is why I wrote out the unit hours here, because you can't just pop in a 5 for T, or else it's going to assume you're working with 5 hours. So first I have to convert my 5 days to hours so that these are on the same units as my T. So there's 24 hours in a day, so I'm going to times that by 24. And I can see that 120 hours have passed. This is now my T value. Make sure it's the same units as P, or else you're not going to get the right answer. So now all we have to do is use our equation from above. And instead of T, I'm going to put in 120. Now you have to put it in your calculator. I'm going to bring up the calculator to show you how you can type it in, just so you don't have any mistakes. So we want to type that in to figure out our answer. So you can basically type it straight in. You have 1,000 times 3 to the exponent 120 over 25. If you have a TI-84, it'll do it like this for you automatically, and you can just hit enter to get your answer. But you have to be careful if you have a TI-83 or an older version of the graphic calculator, because this part here will be a little bit different. It won't automatically put it all as an exponent for you, so you're going to have to include brackets around your fraction. So I'm going to show you how to type it in if you have an older version of your calculator, or if you did this and it didn't give you the same answer as me, then try typing it in this way. And put brackets around your exponential fraction, and then hit, oh, I put in an extra 0. Now you get to see me make a mistake. There we go. 1003 to the exponent, open up a bracket, and it was 120 divided by 25. And then you should get the answer there. So be careful with your calculator. Maybe try that, pause the video and try that for a second and make sure you get the right answer. You should get 195,066 bacteria. And notice how I didn't tell you to round here, but if we're counting certain numbers of bacteria, you can round to the nearest whole number. So we're going to say 195,066 bacteria. Okay, then it says how many bacteria were there 3 days ago? So before all this happened 3 days ago, basically we're going back in time 3 days. So you have to be careful though, we need it in hours. So now we're going back in time. So it's like you're going negative 3 days backwards. And we're going to times it by 24 to change it into hours. And you're going to see that we're looking at 72 hours ago. So you're going to use that same formula. But now your t is going to be a negative 72. So try putting that into your calculator. When you do that and you round it to the nearest whole, you should see that you had 42 bacteria 3 days ago. That one's done. Let's look at another example on the next page. There's different ways we can ask this, so we have to be a little bit careful. So the next question says, after each washing, 3% of the dye in blue jeans is washed out. How much of the original dye remains after 10 washings to the nearest percent? So same thing I always do with all these questions. These are all my variables, and I'm going to fill in what I know. We have to be a little bit careful when it's percentages, and there's a little bit of extra thinking regarding that. So after each washing, 3% of the dye in the blue jeans is washed out. So that means how much is actually there? After a wash, how much dye is in the jeans? So imagine when you start, you had 100% of the dye. So if 3% washes out after one washing, that means you have 97% of the dye remaining. So that is going to be your B value. There's 97% remaining. And all I did there was I went 100% and I minus to the 3% that's getting washed out. So basically I know after each wash, only 97% of the dye will remain. And that's after each wash. So remember your B and your P are matching terms. So it's 97% after each wash. So my P is after one wash. Those two are always linked together. They're usually in the same sentence. After each wash, 3% of the dye is washed out. So you know that 97% remains after each wash. How much of the original dye remains after 10 washings? So we know our p-value is 1 wash. We want to know our total amount is going to be 10 washings. And then you're going to think carefully about your A value. How much dye did you have in the jeans right to start with? You had 100% of the dye. All of it was there. So as percentages, usually your A value is going to be 100% because you're starting with that full amount. And then something happens, whether it's increasing or decreasing from there. When working with percentages, I like to change them to their regular number values. So I'm going to divide both of these by 100. To write it numerically rather than as a percentage. Now I have everything I need and I want to find out what's my total amount of dye that remains. So I'm looking for my Y. So now I'm just going to plug it into the formula. You don't have this version of the formula on your formula sheet. It's just AB to the X, but I just like to think it's T over P, TP, toilet paper. I don't know. That's the way I remember it. So now we're going to plug it in. My A is 1, my B is 0.97, T is 10, and my P is 1. Then you're just going to type that into your calculator. You should get 0.74, but it wants my answer to the nearest percent. So I'm now going to times that to 100 to get my percentage. So that tells me after 10 washing, only 74% of the dye will remain in my jeans. So they're getting a little bit lighter each time. Okay, let's try another one. This one's about caffeine. It says when you consume caffeine, the percent of caffeine left in your body is reduced by 13% every hour after consumption. Okay, so we need to fill out what we can from here and make sure our stuff is in the right spot. So it says the amount of caffeine left in your body is 13% every hour after consumption. It's reduced by 13%. So you started out with 100% of the caffeine in your body. As soon as you drank that coffee, you have 100% of the caffeine in your body. After 1 hour, it's reduced by 13%. That means only 87% will remain. So often with percentages, you're going to have to do a little extra side work and either add or subtract something, depending on the wording. It's not always that case. So that means I only have 87% of that caffeine after 1 hour. So remember, your B and P's are always linked together. 87% after 1 hour. There it is. Okay, so it says write an exponential function that models the percent of caffeine remaining in your body as a function of the elapsed time. So again, with my percentages, I like to write them as their number form. So now we're just going to type in what we know. Here's the general form of the equation. My A is 1, my B is 0.87. My T, I don't know yet, and my P is 1. And then you can simplify this. The 1 in front doesn't really do anything. Dividing by 1 doesn't really do anything. So technically, this is just going to be this once everything's simplified. Okay, then we're going to go on to part B. It says, what percent, the nearest percent of the original amount of caffeine remains in your body 5 hours after consumption? So that's telling me my T. It's been 5 total hours. And then I'm just going to be careful and make sure my units match, which they do. So that's perfect. And then I'm just going to put in a 5 for my T. And then you're going to just put that in your calculator. But it wants to have it to the nearest percent. So we're going to times this by 100 to make it into a percent. That'd give me 49.8%, but we're rounding to the nearest percent, which is 50%. That means 5 hours after you drink that coffee, only half the caffeine is going to remain in your system. Okay, let's do one more. Population of wolves in a forest. So again, it's exponential, so let's figure out what each of these variables will stand for. Population of wolves in a forest increases at a rate of 2.5% per year. So this is going to be your B and your B value here. So you have to be careful. Your B value is not 2.5% because you still have your original population of the wolves, plus you're adding in an extra 2.5% each year. So when it says increases at a rate of 2.5%, your B value, the next year you're going to have 102.5% of your wolves, right? The 100% that were there already plus that extra 2.5% that it's increasing by. So your B value is going to be 102.5%. So again, look for wording. If you see increasing, usually you're adding it to 100%. If it's decreasing or breaking down, usually you're minusing it from 100%. And that's every year. So my P value is 1 year. It says initially there are 240 wolves. That's your A value. So then it says write an exponential function that relates the population and time in years from now. So here's the standard form of it. So we can write it out. We know it's y equals 240. I'm going to change that percent to a decimal. And I don't know what T is, so I've just filled in what I know. And they did kind of clarify they wanted the population as P a function of p of t. So what that technically means is we could have written it this way. Instead of saying y, I could have written it this way. And I mean, I don't have to put that over 1, so that could have been my final answer there. And then it says, what will the population be in 6 years? That means your total time is 6 years. I'm going to just double check to make sure my units match for my p and my t, which they do. And you can just plug it in. So when t is 6, I'm just going to figure this out here, pop that in my calculator, round it to the nearest wolf. I can see that after 6 years, there should be about 278 wolves. And use your common sense too. Like if you had made the mistake of saying 2.5% here, you would have gotten a super tiny number here. And then if you look at the question, it's saying the population of wolves increases and you're starting with 240. So it wouldn't make sense to have like 5 wolves after 5 years if the population's increasing. But this makes sense. After 5 years, we started with 240 wolves, and then we ended up with 278 wolves because it's been slowly increasing each year. And that's it for today. Have a great rest of your day.